Hello everyone and welcome back to ChatCraft. I just cleared the rain. I noticed that the rain is terrible for file sizes, so if I'm trying to upload these and it's raining, the file size becomes massive. Like, I don't know why exactly, but it does. Well, I have a rough idea. It's because of how the video codec I use, basically how it works, how it handles moving pictures and changing pictures and such. And that codec has difficulty handling lots of small raindrops falling down, I would say. But as you can probably see, and I kind of forgot to mention that last time, I do now have Optifine installed, so there is now a sort of beta version for 1.7.2. which I'm not certain if it works in 1.7.4, but I've just rolled back to 1.7.2. The world generation is the same, so it should not be any problem. And I now have the connected textures again, which I greatly prefer to the standard textures. And I'm not going to talk about the controversial topic, which I kind of said I might talk about last time, because since I'm recording these back to back, I obviously haven't heard back from anyone yet. So you can also comment on this video whether you would be prepared to possibly, I don't know, keep an open mind about things. On a matter that's slightly that evokes stronger feelings than the feminism issue. And so today, you've heard me say quite often, or you might have heard me say quite often, that I am not a scientist myself, that I am a mathematician. So, one thing which you, as if you are doing maths, you will hear quite often is that people sort of they believe maths to be a science. They think it's all the same thing. So firstly, I think I should tackle that and tell you that maths is not a science in any way. It is entirely different in its approach. I did a video earlier, I think episode 4, maybe 5, where I was talking about what science actually means, and it's important to note that science has I guess you could call it a large problem. Scientists have to deal with the world they live in. That's what science is. It's trying to make sense of our environment, the world which we happen to live in. Trying to make experiments, trying to draw up theories that explain things, trying to prove these theories wrong, all that is science. But it all has to do with nature, with what we see around us, in some way or form. And that's the one restriction which mathematicians don't have. For example, if a chemist comes up with a nice theory for how certain chemicals react with each other, he might find that a very good theory. I'm not giving any examples, I'm just making up the general point. So you might have come up with this really cool theory. It explains everything you've seen so far, and it sort of looks good. It all falls together and it makes a great deal of sense to you, and it's just a very beautiful theory because it's simple and elegant and explains all your observations. And now the dreaded reality comes along and proves you wrong. Because while you cannot prove a scientist right, you can certainly prove a scientist wrong. And then that beautiful theory which you just made up, it's dead wrong and you can throw it away. And that's a problem that scientists basically tackle every day, because it's sort of how science moves forward. You take a theory someone else has formulated and you try to attack it. You don't just say I don't like it so this is wrong, of course. You you say if this theory were right, we would expect this, for example, this chemical to sort of turn green when we pour water in it. It does in fact turn blue, so your theory can't be right. And then whoever made up the theory might be a little unhappy about the fact that whatever amount of work he spent doing that is just gone to waste now. As a mathematician, you don't face that problem. If you make up a theory, or if you find a law that you find good, you can prove it right yourself, basically. There's very, very few things in maths which are just conjectures. Almost everything that you see, and pretty much, well, everything you see about maths in your school career is proven. And that's because maths doesn't have to deal with reality, which is sort of the problem that scientists have. If reality disagrees with them, they are out of luck. They have to basically accept that reality is right and they're wrong. A mathematician doesn't have that problem, because maths is not a science, it's not based on nature. Like the early advances in mathematics, obviously, they were driven by a desire to sort of quantify nature and understand it, so that's why a lot of the things we do in maths happen to be useful in the sciences. A lot of the calculations end up being relevant for modern physics and chemistry and such. But that's essentially a coincidence. And there is mathematical research, and not small amounts of it, which have no bearing on reality whatsoever. They are just sort of research for the sake of research. They don't try to portray reality, they try to portray something. Which is sort of the point. In mathematics, you kind of invent your own universe, if you like, and then you just go with it. So, for example, one thing that's often quoted is that there's a certain mathematical truth in the fact that 1 + 1 = 2, which, when you say that, you always imply things, basically. You're not really making a generalized mathematical statement. You're saying, in the realm of natural numbers, assuming all the things we usually assume about natural numbers, 1 + 1 does equal 2. And that's correct, in that sense. And that is correct because the number 2 is actually defined to be what happens when you take 1 and add another 1. The number 1 is sort of defined by its properties. It's something that if you multiply it with another number, it doesn't change anything. So if you multiply anything by 1, the result doesn't change. 100 times 1 is 100, 1,000 times 1 is 1,000, 9,000 times 1 is 9,000, and so forth. So that's what the number 1 means. And then we're just saying, okay, so let's assume we take this number 1, which we've defined by its properties. We've also taken number 0, which we defined by its properties. And that is, if we add it to something else, it doesn't change anything. So 0 is to addition what 1 is to multiplication, in a way. You're saying, okay, so I have these two numbers. Let me just go with it. I've got this multiplication so far. But if I do multiplication with the numbers I've defined so far, so number 0 and number 1, by just multiplying these numbers, you'll never do anything. And so you try addition. Well, if you add 0 to anything, it doesn't change. So the only way you kind of get more numbers is if you add 1 and 1. Which, it can't be 0, that would lead to a contradiction, assuming you want the resulting set of numbers to have certain properties. So it has to be, and it can't be 1 either. 1 + 1 can't equal 1, so it's clearly not one of the numbers you've had before. You need to make up a new name for it. Let's just call it 2. And that's sort of it's not the way numbers were originally developed, but it's the way, well, I guess it is the way numbers were originally developed, but it's basically, it's not a mathematical truth that 1 + 1 = 2. You're saying that we get a lot of useful useful applications in reality if we go with 1 + 1 = 2, and then if we add another one, we get a new number, and you're basically saying every time I add one, I get a new number, and then multiplications fall into place as well, and you can multiply numbers and all that stuff. But if you're studying maths, you might at some point encounter the subject of algebra, where it is by no means a mathematical law that 1 + 1 has to equal 2. You're going in a much more general way. You're saying, okay, so addition is something I do with two numbers, so I have a number and I add another one, which is what we do in natural numbers after all, so in everyday numbers. And we just want this sort of connection between two numbers to have certain properties. So, for example, we could say that we want it to not matter if which number we take first. So 1 + 2 is the same as 2 + 1. And again, this is something we assume because it within the natural numbers, which sort of are useful in our everyday world, it happens to be true. If you take one apple and then you take another two, you get the same result as when you take two apples and then another one. You end up with 3 apples. So it's sort of a natural thing to assume that, yes, adding kind of works both ways, and it doesn't matter which way around I write the numbers. And again, that's something which isn't inherently true. It's true within the natural numbers because we defined them in such a way that it is true, but it's not something that's inherently true in all number systems. Again, in algebra, you will often encounter situations where this is not true, where you define something that is an addition. You use the plus sign to denote it, basically, but it doesn't actually have the property that it is. The word is commutative. It doesn't have the property that if you add two numbers in the other way around, it gets the same result. Again, that's just something we took for granted because it happens to work out that way in reality. Well, within the natural numbers, which seem to be a good way to work out certain problems in reality. Oops. Ouch. But as I said, it's not a general mathematical truth, it's just something we sort of say we want to be true, so let's just go with it. And the same is true as for very many things which you consider mathematically correct. But you can get a great deal of theory if you just, for example, you just take the number 0, which we already had. We say, well, if we have this sort of addition, which we define it to have certain properties, we say a plus b plus c. The result doesn't change depending on which of the operations I do first. So if I add a and b first and then add c, or if I do b and c first and then add a, that shouldn't matter. And then you also say that there should be an element which is sort of neutral. So that's your number 0, basically, with addition, because 0 doesn't add anything. And then you also go ahead and say that you have another sort of connection between numbers, which is multiplication, which you usually use a small x to note multiplication. And you say that has to have similar properties, and we sort of want these two to work together, which again, those are the associative laws, which you've probably also seen in school. And then from the multiplication, you also want a neutral element, which you then call element 1. And these are just names, of course. Now, they are names borrowed from the natural numbers because they were the first sort of numbers which were really researched, I guess. So you just use the same terminology because in many ways it's a useful way to think about it. But the number 0 and 1 in general in maths tend to be defined by their properties and aren't necessarily the natural numbers which we know. And as it turns out, if you just have this 0 and this 1 with the, I guess, with the same kind of calculations which you would expect from your everyday school life, so 1 times 1 equals 1, 0 times 1 equals 1 times 0 equals 0, and 0 plus 0 equals 0. And then you just say, okay, 1 plus 1, I don't really want to have more numbers because that would get confusing. Let's just say 1 plus 1 is 1. Wait, no, we can't. Because if 1 plus 1 equals 1, then 1 equals 0, and I wouldn't have two different numbers in the first place, and that doesn't really help, so 1 plus 1 cannot be 1. Well, I've got another number already. I've got 0. Let's just say 1 plus 1 is 0. And you can get a lot of useful theory out of that. It's actually the smallest field. Field is a mathematical term for a sort of set which has certain properties. The real numbers which you encounter in everyday life, they're called real numbers, basically. Those are a field, and but all the properties you demand of this field is also present if you just take 0 and 1 and say all the usual stuff, and 1 plus 1 equals 0. And if you think about it, it's not that far-fetched in a way. Consider a circle. Let me just quickly make a circle. A very small circle. Alright, and let's just say this is a terrible circle for my example, so I'll make it bigger slightly. And this won't be a very pretty circle. It won't be a very circular circle even. Okay, so let's just say this is a circle, and this is the center. So let's just say, okay, so let's assume over here we have a sort of number. And then over here we have another number. We have these two elements, right? And they're on the circle. And if we add two numbers, we just understand it as going around the circle again. So if you have your number 0 and you add the number 0, you don't go anywhere. If you have number 1 and you add the number 0, which you assume this to be the 0 line, I guess. So this is on the 0 line, so you don't have to move anywhere to get to this point from your starting position. And to get here, from your starting position, you have to go 180 degrees. It doesn't matter which way, but so we might as well choose one way. So what happens if we take this point 180 degrees away from that and do it again? So we basically add 1 and 1. Lo and behold, we're at 0. So basically, if we're understanding our operations as movements on a circle, then 1 plus 1 can easily equal 0. And you don't have to stop there. You could, for example, say, okay, 1 plus 1 equals 2, fine, I'll give you that. But I don't want any more numbers. So 2 plus 1 is just equal to 0 now. Which means basically you're going a third of the way around the circle and another third, and if you do a third again, you're just at the starting point again. And you can get a lot of useful stuff out of that. For example, modern computer encryption is sort of a rather remote, I guess there's a lot more theory coming after it, but it sort of works on the principle of these things. They're called groups. Well, the ones I just gave you are actually examples of fields, because you don't only have the addition, you can also define a multiplication which is meaningful on that set. But basically the most simple mathematical structure, which only has one connection, which we usually call addition, that's called a group. And just based on that theory alone, which we don't even have a multiplication, we're only adding. And very often we're adding, but at some point we're saying, okay, we've gone back to the beginning now, we're just going to call that 0 again. And from that you get a lot of modern encryption algorithms. They use those sort of principles. So it's not necessarily a pointless endeavor, but it doesn't have a bearing on reality intentionally. It is at some point research just for the sake of research. I've heard scientists often say that mathematics is the language of the universe. And that's sort of true, because as it happens, mathematics can be used at times to talk about things in the universe quite well. But there's points where it just breaks. For example, we have this sort of notion of our three-dimensional space as being a Euclidean space with basically that means that if you have 3 coordinates, you can use 3 coordinates to pinpoint you any location. You've got the x, y, and z axes, just like you have in Minecraft, in fact, x, y, and z. And giving those 3 coordinates will tell you exactly where something is. And sort of straight lines are straight lines, parallel lines are parallel lines, all the things you were taught in school, basically. All these things are true. That's what you call a Euclidean space. And as I said, it's sort of got its uses, and it's a good approximation, as we heard earlier, of how our universe looks. And then there's something else in mathematics called the axiom of choice. And the word axiom tells you it's something you have to assume. Can't really be proven. And that states that if you have a family of sets, so a set is just a container thing, basically, which contains elements. So if you have a family of non-empty sets, you can choose one element from each of those sets. That's what it says. And it seems sort of obvious, right? If you have 10 baskets full of stuff, you can take one item out of each basket. If you have 10 jars full of sweets, you can take 1 sweet from each jar. Unless one of them is empty, but we're saying they're all non-empty. So for finite sets, that's completely for finite sets and a finite number of sets, that's not an axiom, it's obviously true. And you can prove it to be true. The problem comes when you reach higher levels of infinity. Something that's more infinite than the natural numbers, for example, which, yes, is meaningful. I might talk about that later if you want me to. But basically, if you reach that point, it's not as obvious. You can't really prove it. Okay, it seems very reasonable. So most mathematicians agree that yes, it is in fact true, and if you think about it, it seems sort of obvious that you could do this. You could just look at each set and just pick one element out of it. From that we conclude, however, that if we take a sphere in this 3-dimensional space, we can cut this sphere up into a finite number of pieces and rearrange these pieces. We're not changing the pieces, we're just moving them around, rotating them. So we're just rearranging these pieces and put them together into 2 spheres of the same size as the original sphere. And we didn't have to use infinite pieces, a finite number of pieces. We don't know how they look. It's a theoretical thing. We can prove, however, that if we take the axiom of choice to be true, we can find such a way to cut up that sphere without actually constructing it, without telling you how to cut the sphere. We can tell you it's possible. Basically, it works by you sort of cut up the sphere into pieces which are so strange that you can't reasonably give them a volume again, so they just don't really have a volume, and you can rearrange them and merge them together and the volume changes, basically. And that's obviously not true in reality. It's ridiculous. But it's what mathematics tell you is possible. So that's one example of a thing that is true in mathematics, but is obviously not the language of the universe. It doesn't help you explaining anything around us, and it's not something to do with the sort of quantum mechanical effects of stuff popping into existence. It's literally saying, I will give you a sphere, cut it into a few pieces, move them around a little bit, and now I have 2 spheres. And that's not the quantum mechanical thing at all. So I guess it's just a point to illustrate, firstly, that mathematics at times reaches conclusions which are true, but utterly pointless, and have no bearing enough on reality. So, yeah. And I'm guessing that's probably enough for an episode. I'm just clearing rainforest right now. I hate that building, by the way. But, yeah, let me know what you think about this. If you have any input on this, if you, and again, if you didn't already, tell me why you didn't say anything about the cosmology. So, I hope you enjoyed, and I'll see you soon. Bye bye!